All right, so why don't we, now that we have really now 3 times talked about the conceptual approach to a single sample experiment, and I'm sorry for doing it so many times, it's really important. Now that we've done that, let's talk about actually calculating a single sample t-test, which is going to be the test we use for the analysis of an experiment under particular conditions when it has single sample. Let's talk about it. So let's talk about performing the single sample t-test. We're going to go through a series of steps here and then talk about each of these steps in some more detail. But I want you to keep in mind that these steps will be basically the same steps for every inferential statistic we do moving forward. They were the same for the single sample z-test, which I introduced to you last semester and then kind of reviewed early this semester. They'll be true of the ANOVA or the f-test. They'll be true of the chi-square. They'll be true of a Mann-Whitney U or a Kruskal-Wallis H. Any kind of statistic you can think of that's inferential is going to go through these basic steps. So what are they? 1, we're going to determine our statistical hypotheses. What we expect the numbers to look like if our null hypothesis is true and if our alternative hypothesis is true. We're going to check the assumptions of the test, which is a fancy way of saying we're going to make sure that this is the right test for this job. We're going to calculate our obtained value, which is going to be a standardized score calculated based on our sample's mean. We're going to choose our alpha rate, which is going to be our proportion of the probability of a type 1 error. It's also going to tell us how probable is too improbable to belong on the distribution of the null. We're going to calculate the t-critical, which will serve as our region of rejections border. And then we compare that obtained value to that critical value on the distribution of the null and decide whether our null hypothesis is supported or not. Okay, let's talk about each of these in a little bit more detail. So let's start with the statistical hypotheses. We've talked about this before, right? There are 2. H sub A, which is our alternative hypothesis, and H sub 0, or sometimes H sub O, which is our null hypothesis. The alternative hypothesis predicts that our IV had an effect on our DV. The null hypothesis predicts that it did not. Now, we can have 2 different types of hypotheses. We can have what's called a two-tail hypothesis, which doesn't predict any direction here. When it comes to the alternative hypothesis, that would look something like this. We're predicting that our mean of our sample does not equal the mean of our population. That means we expect that our sample has changed from our population from which it was drawn because of the manipulation of the independent variable. The sample mean will differ from the population, again, presumably because we've manipulated some sort of variable. We talked about that in the last lecture. Now we can have a two-tail null hypothesis as well. And that's simply going to say that our mean of our sample does not differ at all from the mean of our population, meaning we drew the sample, it was the same, and it's still the same. And we presume it's still the same, that it doesn't differ from our population because our independent variable had no effect. We manipulated a variable, it didn't do anything, so our sample is just the same as it was, which means it's just the same as the population. That's a two-tail example. It's called two-tail because we're not predicting which side of the distribution this will fall. It could be on the bottom end of the distribution or the top end. Now, if we do predict which tail, if we do predict the direction of the change, we call that a one-tail type hypothesis. So in the case of the alternative, that might look like this. We predict that the sample mean is larger than the population mean. That whatever we've done has increased the DV as the result of our manipulation. So, hearkening back to our ABC mouse, we're predicting that their reading scores will have improved. The sample is now better than the population because of what we did. The one-tail null hypothesis, I'll say so in a moment, is the opposite, of course, but first let me say this. The sample mean will be greater than the population. Do you see how I did that? I made a mistake and then I played it off like I didn't. Did I fool you? I didn't. The one-tail hypothesis, the sample mean is larger than the population mean because we presume that our IV has changed the DV for that sample. Now in the null hypothesis, the one-tail is the opposite, as I said. We would say something like the sample mean is less than or equal to the population mean. Because to say that it's not greater means that it could be less or it could be the same. So we have to be a little more careful with our hypothesis here. The sample mean will be greater than or equal to, forgive the typo there, the sample mean will be greater than or equal to the population. So this is how both one- and two-tailed statistical hypotheses work. What about the assumptions? I remind you that we call assumptions the things that we presume, or I guess I should say assume, are true of our population and our sample for a test to be appropriate. Look, if you're hanging a painting on the wall, you check, do I have plaster? Do I have drywall? Or is there a stud behind here? The type of screw you use is dependent upon the type of wall you have. The type of statistic you use is dependent upon the type of data you have. So, what are the assumptions? What things must be true for the single sample t-test to be the right test? Number one, our dependent variable, our DV, is both normally distributed and is data that is interval or ratio. If we don't have interval ratio data or if we have skewed distributions, we can't use this test. I've said this now a long time ago, so you may not remember it, but these two assumptions are called the parametric assumptions. We see them over and over and over again. So remember, the parametric assumptions, the DV is normally distributed, and we have ratio or interval data. What else? Well, the second one's based on the methodology we use. For a single sample t-test to be appropriate, well, we have to have a single sample. We've randomly selected one sample of participants from our population, and we've exposed them to one manipulation of our independent variable, one condition of that independent variable. In our earlier example, we drew a sample of kids from a population of kids, and that sample was manipulated by having been given a free account for ABC Mouse. Here's the third thing that must be true. We must know the mean of the population of raw scores. We need to know those scores as a comparison. Now, it says this in a fancy way. We know the mean of the population of raw scores obtained under a different condition of the IV. That's a fancy way of saying we need to have an understanding of the population before our manipulation. What did those kids look like before on reading, before we gave them ABC Mouse? Because we need to be able to compare them. And the other thing is, and this is almost kind of an anti-assumption, this next assumption makes a juxtaposition between the t-test and the z-test. The t-test allows us to estimate the standard deviation of the population. We can do that based on the sample. If we don't have the actual standard deviation of the population, we can estimate it. So this is an advantage over the z-test. The reason your textbook author doesn't teach the z-test is it's really hard to use. It's a single sample test, but you have to know both the population's raw score mean and its standard deviation. And the truth be told, we very rarely do. So this gives you a hint as to how this calculation is going to go. We're going to have to figure out an estimate of the standard deviation of the population as part of this calculation. So let's talk about that calculation. So what are the steps? And it's another example where these steps are going to look very familiar as the semester goes on because we're going to be repeating them. The first thing we're going to do is we're going to take our sample mean and convert it to a standardized score. I remind you that standardized scores allow us to compare scores from different places. You can compare a score, say you have an older sister like I do. I can compare my sister's SAT score, which she took 5 years before I did, to mine, even though they're from different populations. by converting them so that they're apples to apples. So we're going to convert our sample mean to a t-score, which we're going to refer to as the t obtained. Now I want to show you what's we've come to know as the definitional formula, which explains to you what this score actually represents. And you can see here, the t obtained is equal to the sample mean minus the population mean divided by what's called the standard deviation of the mean. This is not how I want you to calculate it. I want you to use what's called the computational formula, and that's this here. The sample mean minus the population mean divided by the square root of the standard deviation squared divided by n. That's how we're going to calculate the t obtained. Fortunately, we know how to do all of this. We know how to subtract, of course. I'm not insulting you. But we also know how to calculate standard deviations. You know, that's that denominator there, the square root of the standard deviation squared divided by n. Standard deviation squared is the variance, remember? So what we're really calculating here is the variance divided by the square root of n. It's the same thing. So the sample mean minus the population mean divided by the square root of the standard deviation squared divided by n. Now the formula is easy enough, but you won't really get it, of course, until we walk through a calculation together. I'm going to do that at the end of this lecture, and we're going to do it in person on our Thursday together. Once you've calculated your t obtained, what do you do next? Thinking back to our steps. Oh, well, let me say this first. We're converting a sample mean into a t-score, and that's going to allow us to compare that on the distribution of the null. You know that. That's step 2. What's step 3? We got to choose our alpha. And I remind you that the alpha is the probability of rejecting the null hypothesis when the null hypothesis is true, which is a fancy way of saying type 1 error. This sets our level of comfort with error. How unlikely is too unlikely for the t obtained value to belong on the distribution of the null? In other words, we're going to take the distribution of the null hypothesis and we're going to set aside our alpha level as our region of rejection. So in this diagram, the region of rejection is 2.5% on one side, 2.5% on the other side, for a total of 5%. That's an alpha of 0.05. 5%, 0.05. So we make that number, I started to say we make that number up. That's not true. We don't make it up, we select it. And 0.05 is going to be our typical standard alpha level. It means that we have a 5% chance of making a type 1 error. That's not good. We'd rather it was 0%. But this is all based on probability. So we've decided that 5% is good enough. It means we have a 95% chance of getting this right. And we're going to take our chances with that. Having selected our alpha, we use it to establish our region of rejection by determining our t critical. Now I'm going to walk you through this table 7.1 in your text, when we walk through the calculation. But I want to remind you that the t critical value is the border of our region of rejection. We need table 7.1 to figure it out, along with the alpha and what's called the degrees of freedom, which is our n, big N, minus 1. So in the example that comes from your textbook, our degrees of freedom are 24. Our alpha is 0.5, two-tailed, and that creates a region of rejection that is bordered by plus 2.064 and minus 2.064. A score beyond, above 2.064 and below a negative 2.064 lands in our region of rejection. I'm zooming in here on this now, probably too late, but you can see here on the left, you have the degrees of freedom. In this example, our degrees of freedom are 24, which means our n is 25. You can see that we've selected to do a two-tailed test. We're using a two-tailed hypothesis. And we go across the top to find 0.5, and then see where the grid meets. And the arrows show you that. Degrees of freedom of 24 meets an alpha two-tailed of 0.5 at 2.064. So returning to this again, we put 2.064 on the right, negative 2.064 on the left. Yes, I know those numbers aren't right, but play along with the example. So we have negative 2.064 as our border on the left, positive 2.064 on the right, and then we see where our t obtained falls. You've seen this figure a couple of times. If our t obtained falls here, it's not in our region of rejection. If our t obtained falls here, it's not in our region of rejection. What does that mean? It means that these scores, though they're different than the mean of the population, are still close enough to that mean population to believe that they probably belong here. That we can't say that our IV had an effect on our DV. Or in other words, we fail to reject the null. I'm sorry, my dog just saw another dog. If you can hear, that's Betsy barking. Her name's Betsy Ross. My family, for whatever reason, has always named all their dogs after historical figures. I started to say name their historical figures after dogs, which is weird. So as a kid, I had Sam Houston, Lady Bird Johnson, Susan B. Anthony, my dear heart, Abigail Adams, who I had for 16 years, who died 6 years ago in March, and now Betsy Ross. So that was Betsy Ross. My apologies. So you see here, these two values, if these are our t obtained, we're not going to reject the null. If this is our value, it falls in the region of rejection. Or if this is our value, it falls in the region of rejection. And that tells us that, you know what, we don't think these scores belong here because look how rare they are. Look how far out on the tails they are. Look how low the probability is that they belong here. So this is how we're going to make the determination, whether to reject the null or to accept the null. The scores that fall inside our region of rejection or beyond our critical value, said better, get rejected. Those that don't, we accept. So this value, we accept the null. And then this value, we reject the null. I've shown you this exact slide, I think 3 times now, and I'm sorry. But I really want the logic of this to stick. But as I just said a few moments ago, it's not going to stick until we do these calculations. So let's do one right now. Are you ready? I'm pausing for effect. I know you can't answer me. Okay, let's do it. Hey, I mentioned I have a new app that allows me to record directly from my iPad as we walk through a problem. I think it was created for people recording themselves playing video games, which seems like a much more fun use of this particular app. But I think it's going to work for us. What I didn't take into account is the fact that I can't see through my bangs because I haven't had a haircut in 7 months. I don't know if there's an app for that, but we'll worry about that another time, or really you won't. I'll continue to worry about it. So here's the question. We ask whether a new version of our textbook is beneficial or detrimental to our students' learning statistics. On the National Statistics exam, the population mean was 68.5 for students using other textbooks. A sample of our students using our new textbook has the following scores, and you can see those scores there. The first question is, what are the null and alternative hypotheses for this study? So that's A. A couple of things I want to point out to you. It says we're asking the question whether our new version of our textbook is beneficial or detrimental. That word or is important here. This is a two-tailed hypothesis, meaning we're not predicting whether it's better or worse. We just want to predict whether it's different. So, what's our alternative hypothesis? Our alternative hypothesis is what we would predict if our textbook differs from the population, meaning our sample is different because they're using a new textbook. So it might look something like this. Our population score, here, I'll actually rewrite it. Our population, I'll just keep rewriting it. Our population does not equal our sample. Mu does not equal M. My handwriting is atrocious. I apologize for that. That means that we're predicting there's some sort of change. The sample, having used a different textbook, is either better or worse, but what we're predicting is it's not the same. The null hypothesis, of course, is the opposite of that. as you can hear Betsy barking in the background. The opposite of that is that the textbook had no effect, that it didn't matter. And if it didn't matter, then our population mean should be equal to our sample mean. These are our hypotheses. I accidentally called that B when I shouldn't have, because this is all still part of A. So I'll just erase that here in real time. But for A, here are our hypotheses. We hypothesize that our textbook will make a difference. That's our alternative hypothesis. So the mu does not equal the M. Our null is the reverse, that our population mean will equal the sample mean because it didn't make any difference. Okay, so that's A, piece of cake. Now here's the tricky bit. We have to calculate T obtained. And what I did was I put our formula for T obtained here on our page so we can kind of see while we're working what it looks like. There you go. And you can see that T obtained equals the sample mean minus the population mean divided by the square root of the standard deviation squared divided by the n for the study. Now there was no reason for me to write that there except out of habit, so I will go ahead and erase that. And in fact, if I'm able, I'll just edit this out so you'll never know that I did such a dumb thing. But let me just erase that out. There we go. So let's calculate T obtained. If we're going to calculate T obtained, what we need to do first is calculate the mean. Let's do this. Let's make a column of X. This will look familiar to you. Column of X, and we'll put our X scores: 64, 69, 92, 77, 71, 99, 82, 74, 69, 88. That's our X scores. Now our N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N is 10. And so to calculate the mean, of course, we take the sigma x. Handwriting is criminal. Sigma x divided by n. So all we have to do then is figure out what sigma x is. So sigma x equals the sum of this column. Let's do this. Let me bring up our calculator. And we can do this math, and you can kind of keep an eye on me to see if I get it right. 64 plus 69 plus 92 plus 77 plus 71 plus 99 plus 82 plus 74 plus 69 plus 88 equals sigma x is 785. So the mean will be 785 divided by 10, or the mean equals 78.5. It's a nice thing about having an n of 10. Makes that division problem very easy. Okay. Switching back without the calculator, now we will make an x squared column. Do you remember this? We're going to make an x squared column because of right here. Right here what we have is our standard deviation calculation. And it's a little different than you remember. There was some confusion last semester, and it was my fault. I never really clearly explained it to you. That sometimes your textbook would have an n-1 in the denominator, and sometimes it wouldn't. It depended on whether you were estimating the population. Well, from now on, we're always estimating the population. So this is going to be your standard deviation formula. You can see in that formula we have sigma x squared. So we have to get the sum of this x squared column. So basically what we need to do is bring back our calculator. I shouldn't have made it go away. And we're going to square each of these numbers. 64 squared, I don't have a squared button here, is 4,096. 69 squared is 4,761. 92 squared, 8,464. 77 squared, 5929. 71 squared, 5041. The column's slowly drifting left. 99 squared, 9801. 82 squared, whoops, 6724. 74 squared, 5476. We already calculated 69 squares, that's 4761. And then finally 88 squared, 7744. So now we're going to sum this up, and the sum of this column will give us sigma x quantity squared, which we can plug into our formula. So sigma x quantity squared is going to be, we're going to work from bottom to top. 7744 plus 4761 plus 5476 plus 6724 plus 9801 plus 5041 plus 5929 plus 8464 plus 4761 plus 4096 equals, it's big numbers, 62797 sigma x squared. It's really unfortunate that these are so big. That is the sum of sigma x squared. The other thing we need is sigma x quantity squared, which is 785. You can see that number here, 785 squared. 785 times itself, 616,225. Let me make a promise to you, a solemn promise to you, that you'll not have numbers like this when you do these on exams or even homework. Okay, so standard deviation equals the square root of sigma x squared, 62,797, minus sigma x quantity squared, 616,225, divided by n, which is 10, all divided by 10 minus 1, which is 9. Okay, so we'll do this part first. First part here. 616,225 divided by 10 is 60. Oops, I lost my pen. Square root of 62797 minus 660 22.5. 61,622.5. All divided by n. So we'll do, as we scroll down a little bit, we'll do this part next. I want to emphasize that this whole thing is square rooted here. So let's do this arithmetic real fast. 62,797 minus 61,622.5 equals. Now we've got the square root of 1174.5 divided by 9. So let's do that. 1174.5 divided by 9 equals 130.5, which we take the square root of. And the square root of 130.5 is difficult for me to find. There's a way to switch this, right? There it is. 130.5 square rooted is 11. Standard deviation equals 11.42. There we go. That was easy. Those are big numbers, right? But don't let those big numbers scare you. It's the same thing we've always done. We just simply calculated this formula right here. So let's take this. I think I can make that go away. Let's take this and move it down. Okay. We've got our T formula. I hope you enjoyed my dragging the formula sound as I brought it down to the bottom of the page. But in doing so, I accidentally turned my iPad off. So we got a little bit of a a smash edit here. Look, I'm not a filmmaker. You know, I'm not Martin Scorsese. And look, if I were a filmmaker, I'd be bad at it, to be honest. But I'm doing the best I can. The good news is I know about statistics, and here, that's what we're up to. You can see here that we've basically got everything we need for the calculation. Well, for t obtained, it equals the sample mean, which we calculated. We can scroll up and find it. It's right here, 78.5. Minus the population mean. Now, we didn't calculate that. Remember, the assumption is that we know that, which means we have to be given it. It is 68.5, you can see there in the problem. Divided by the square root of our standard deviation squared, or the variance if you want to be fancy, 11.42 squared, divided by the square root of n. I remind you that n is 10. So divided by 10. Okay, so let's bring our calculator back real fast. This calculation's super easy. If I can get my calculator to work. There we go. So 78.5 minus 68.5 is 10. We had all those ugly numbers, but now you can see the math's going to be nice for us. It's kind. Let's take 11.42 squared, which is 130.42. We're going to round to the 100th place here. Divided by, still square rooted, divided by 10. So 10 divided by 130.42 divided by 10. I can't believe I just put this into a calculator. You can laugh at me at your own pace. That is, of course, 13.042. So we want the square root of 13.042, which is 3.611. So 10 divided by 3.611. Which gives us a t obtained equaling 2.769. So we'll say 2.77. There it is. That's the value, the t obtained value, that we're going to place on our distribution of the null to see where it falls. But the first thing before we do that is we have to determine our t critical. Let's scroll up and read what it wants us to do here. It said B, compute t obtained. Okay, we've done that. Check. T obtained equals 2.77. And then it says C, determine your t critical with an alpha of 0.5. Cool. Here, we'll do this again. Premature. That was me. That wasn't some kind of fancy computer. This is our value. Bring it even further down. Doop. Okay. We're just going to bring it to the next page. This is our critical value table, C.4 in your textbook. And let's see. We have an alpha of 0.5 according to the question. So that's right here. Degrees of freedom is n minus 1. Our n is 10, so degrees of freedom is 9. So where do these two meet? Right here. 2.62. 2.262. Let me do that again. 2.262. So if we take our distribution of the null, we would draw it like this. This is what we would expect to be true. We would expect our data to look like this if our null hypothesis is true. It's two-tailed test. So we're going to put our values. Did I do it as a two-tailed test? He double checks his work. He did. Good job for me. This is a positive 2.262. This is a negative 2.262. Any score that falls here and beyond or here and beyond, we reject. That's the region of rejection. Any score that doesn't, we fail to reject. So what's our t obtained again? 2.77. 2.77 falls right here. So what does that mean? That means that this score, 2.77, probably doesn't belong on the null distribution, because remember, this is the distribution of the null. So what that means is we are going to reject, I accidentally erased that, but it actually almost works okay. We are going to reject the null. Because that score doesn't belong there. Now, what was the actual question it asked us? What is part C? Let's put this first. C asks for the t-crit. And the t-critical is, scrolling all the way down, 2.262. Forgive me for not having the memory to be able to remember that. Equals 2.262. And then it says, what do you conclude about the use of this book? Well, what we concluded, y'all, was that our score falls here, that we reject the null hypothesis. What that means is we are going to presume that our alternative hypothesis is true. That, in this case, that our sample mean does not equal our population mean. In other words, our textbook changed statistics scores. Our sample differs from our population due to the fact we gave them a new textbook. In fact, they improved. So, we have supported our alternative hypothesis. We haven't proven it, but we've supported it by rejecting the null. And by the way, you're always going to put this in the language as saying you reject the null. Now, the way we report a t-score is this. We say t, degrees of freedom, which is 10, equals the t obtained, which we calculated to be, scrolling up again because of my memory, 2.77, comma, and then you put p for probability. Now, if you reject the null, you say less than your alpha. That's statistically significant. That's what that means. Now, if it was non-significant, we would have said this, p greater than our alpha. And we would have failed to reject the null. But that's not what it was. So we'll just cross that out like it never happened. Okay, a little sloppy using this app the first time, but I think you get the idea. We'll do another one together. We'll do it in Zoom. And I'll try to make the numbers easier. Foolish of me to have made such complicated numbers. Okay, enough. But I hope you enjoyed it. I'll edit this out. I'm an older fella. I graduated from college in 1995. And I did my first single sample t-test in 1993. And I've kind of been doing them ever since, mostly as a professor, occasionally in research. So it is hard for me sometimes to know how complicated it is because I've just been doing it so long. When my mom was alive, I tried to teach her to use a computer mouse one day. And she started picking up the mouse and moving it around with her hand in the air. And I couldn't believe it. But then I realized I never explained it to her. It was so obvious to me how a mouse worked, I never explained it. I worry a little bit that sometimes the statistics are like that because I've been doing them so long. But I hope that it wasn't too bad. And as I've said now so many times, you're going to get lots of practice, including when we meet in lab. Okay, that's the single sample t-test. We're going to start talking about experiments that are not for single sample experiments, but the much more common and truthfully the much more powerful two sample experiments. Because it's those two sample experiments that really allow us to determine causality. Meaning, did this thing cause this other thing? I mean, that's the goal, ultimately. So let's do that soon. Okay, be well. Bye.